عليكم أهلا وسهلا بكم في مساق Fundamentals of Renewable Energy. نلخص آخر محاضرة قمنا فيها. We explained the basic principles of wind power generation based on a tin disk. We explained the maximum power produced. We learned that wind turbines with a large number of blades do not necessarily produce more power. We said basically three blades are more suitable than three or two blades are more suitable than numerous blades. We learned that large rotation speed do not necessarily yield more power. We estimated that the maximum power you can get is around 59% based on the wind speed and the wind that goes through the blades. Now we're going to talk about power production, energy yield of a wind turbine and farms. If we know the power curve of a wind turbine, power produced by the wind turbine for each wind speed, we also know the wind characteristic at the turbine location represented by the histogram or showing how many times a certain wind speed occur at the location. Then the product of these two curves give for each wind speed the total power produced. So in order to know the total produced power, we need the wind curve, uh, the wind speed, and the characteristic at the turbine of the wind at the turbine location. That means these three will produce or will give us the total power produced. Thus, zero power cut, zero power cut in speed, then positive value for the other ranges of the wind speed. Then we have the cut of speed. So the cut in, when we start producing power, we hit the maximum in the middle, and we end up with the cut off speed. Generally speaking, if we know the power curve of the turbine and the characteristic at the location of the turbine, then we can compute the energy yield. Basically, here's what we're showing. We show if we know the velocity of the wind, then we look at this and the speed of the wind, usual the velocity. We have a cut in speed. This is the minimum speed to produce energy, and the cut out, that's when the turbine turn off. This is when the turbine turn in. Here's when the turbine turn off due to the dangerous of the wind speed. Do you have turbine data? Do you have wind data? If we have the turbine data and the wind data, then we can estimate the maximum power we can get. Energy yield calculation. Do we have nothing? Energy yield equal hours per year times the installed capacity times the capacity factor. Usually the capacity factor for onshore is around 25%. For offshore it's a little bit higher. It's between 35% to 45%, depends on the location and the depth of the offshore facility. The capacity factor is an indicator of the percentage of the time a wind turbine runs at full speed. That means, or full power. That means uh, during the day or the 24 hour, uh, how often is the power turbine runs full power. Using the rated power of the turbine, we can multiply this value by the capacity factor to get a rough estimate of the energy yield. Uh, Usually, when you talk about wind turbine, you talk about wind turbine farm. Does this farm produce 10 megawatt? Now, if you look here, we have 10, but we get to know how these wind turbine affect each others, because usually the velocity of the wind is slowed when it goes from one turbine to the other if they are in line with each other. If we look at the curve here, or the figure here, we notice that the wind usually at the low altitude here is slow. Once we go up, as this is the characteristic of the wind, it start going, we start seeing higher speed. Now, we know that the blades create a disk, and the wind which goes through this disk, it generate a torque or a force that will turn these blades on, or it will make them move, thus generating force, and this for mechanical force, then this force is converted to electrical force. Now the wind that goes through this disk, hypothetical disk, will slow down. The one which goes around stays with its original speed. Onshore, the decrease mean wind speed spacing between each turbines will have a negative effect on the wind speed. Usually, sometimes it creates a turbulence, which means the wind start going around each other. It's like a circle, especially for tall turbines. When you talk about offshore, the distance is usually 3 to 5 diameters. If you look at the offshore, it's a little bit lower. Larger spacing is required. It's between 5 to 15-meter diameters. The wake effects, this is what we're talking. This is increasing turbulence, reduce wind speed. Usually, when you align, as you can see here, the wind goes through. Basically, this is in this area, the wind speed is reduced. Usually try to align your turbine with the wind, so it takes the maximum, or generate the maximum amount of force or torque, so you produce more power. So geometric configuration helps to reduce the wake effect. So basically, what we have done today here, we're talking about the wake effect, which reduces energy production of wind farm. An explicit model for wakes is used to evaluate the impact of the wake effect. Geometric configuration helps to reduce the wake effect. One turbine location could increase its energy production. The next segment of the lecture, we're going to talk about the electrical system. Okay. Electrical system from main shaft to the power system. The mechanical energy has to be converted into electrical energy and fed into the power system. Usually wind turbines produce mechanical energy. This mechanical energy has to be converted to electrical energy, and through some transformation or conversion it will be fed into the power system, what we call it the grid. To make this connection it is required the electrical system. The turbine has a power curve, and that power must be converted into electrical power. As you can expect, the turbine does not produce rated electricity on consistent basis, or it does not give full power at all time. This system has to operate at varying speeds. If it operates at varying speeds, that means the power produced will vary. The power has to be supplied to the power system at the voltage and the frequency of that power system. If we're talking about a transmission power system or distribution power system, then we have certain voltage and certain frequency that has to be matched. This has to be done in a cost-effective way. Basically, we're producing, if we want to have a system and everybody believing in that system, then it has to be cost effective. There are all kinds of control, protection, and safety system around this. So we have to have control to control when we turn the power on, when we turn it off, when to isolate the system. We have to have protection in case something wrong happens, short, or the wind goes over speed, over the cut out speed, and we have to have safety around the system also. The requirements for an electrical system. The electric system that makes this connection can be divided into two parts. A part inside the wind turbine called the generator system. This system converts the mechanical power into electrical system. A part outside the wind turbine called the collection and transmission system. So we have a power curve, we have a speed range, and both will produce the power. The voltage and frequency for the grid connection is required here. Minimum cost of energy. We've got to find wind's cost when we should use this this wind energy. Control, safety, and protection components. From main shaft to the power system. We're talking about this. This system collects the power within a wind farm and transmit it to the power system. In the wind turbine, different generators are applied. We have two types of generator, geared system, the geared drive system, and direct drive systems. In gear drive system, the mechanical speed of the main shaft is increased roughly 1500 rpm. A generator converts the mechanical power into electrical power. In direct drive system, the generator is directly driven by the main shaft rotating at a very low speed. So basically what we have two systems. The gear one is for the high speed. The direct drive system is for the low speed. The gear drive system, as shown here, we have the gearbox. This is the main difference. We have the generator, the converter, and the power system. So the main difference between the two systems, the gear drive and direct drive, is the gearbox, which raises the speed to 1500 rpm. Power electron converter. Both systems need a power electron converter for the connection to the power system. The generators operate at varying speed and therefore generate at a varying voltage and a varying frequency. The power system has a constant voltage and a constant frequency. That's one of the main reasons when we talk about renewable energy, we're saying it's not a reliable energy because it does not have like typical power station, fixed voltage and fixed frequency. A power electronics converter converts the varying voltage and frequency into constant voltage and frequency. At full load, the typical efficiency of gearboxes, generators, and power electron converters are in the order of 97%, very high efficiency. At partial load, these efficiency may decrease, especially for gearboxes. Here we have a geared drive Nordex N117 3000. This gives us output 3 megawatt. We have here this is how it looks. It has a generator inside. The gearbox is here, and this is the blades as you can see. Direct drive in Enercon E126, it produced 7.6 megawatt. The diameter of the generator is in the order of 10 meter. Because the generator is so large, the nacelles is built around this generator, giving it different form. For a single onshore wind turbine, it is connected to the power system using a transformer to increase the voltage level of the generator to that of the power system. So basically, for onshore, it's not that hard. For a wind farm, especially offshore, this is more complicated. In a wind farm, the generated electrical power is converted to the right voltage level and then it has to be transmitted to shore. Basically, as you can see, most of these offshores are far away from the shore, so we have to transmit the power produced there to shore where it is needed and it can be consumed. They mainly depends on the distance to the power system onshore. A collection and transmission system, we're gonna look at Egmont and Z, the offshore wind farm. Egmont and Z, abbreviated as OWEZ, has a power of 108 megawatt. At 10 kilometer offshore, it is relatively close to shore. In this case, the power is collected at a voltage level of 33 kV and transmitted to shore at the same voltage uh, and transmitted to shore at the same uh, voltage. Let's see, where did we go? Okay. We're gonna look at Prince Amelia, which is produces a 120 megawatt. It's located 23 kilometer offshore. In this case, after the power collection, the voltage levels is increased to 150 kV to transmit the power to shore. The voltage is increased to reduce the transmission losses. As we know from power system, the higher the voltage leads to lower current and the transmission losses are proportional to the square of the current. That's why we reduce the losses of the system. Brad's offshore is one is 400 mega produces 400 megawatt and it's 90 kilometer away from the shore. It can be classified as far offshore. In this case, After the power collection, the voltage level is not increased but converted from AC to DC using power electronics. The reason to use DC for power transmission is that using AC at long distance is not feasible because of the large reactive power consumption of the cables. Because the offshore power system does not yet exist, a lot of research is done to investigate the best offshore power system would look like. The future trend going to deep water and high altitude. Uh, as we know, the future of wind energy is not onshore, it's the offshore. Typical of offshore foundation, a newly installed foundation in Europe, their offshore foundation, there's two major foundations. One we call it monopoles structure and the other is jackets. In 215, 90% of installed foundation were monopoles, 3% were jackets. If we look at this figure in 2018, we notice 60% monopoles and 37% jackets. That means the jacket structure is starting to pick up. Its share is higher than in 215. In 2018, we notice the number is of the jacket increase, and we're gonna notice why. Manifolds usually they're suitable for not so deep water, usually less than 30 meter depth. And if you look at it, the type of sand here is stable. What we call it is stable. And it's basically the diameter of the manifolds is around 30 meters and it weighs around 1 ton, 1,000 ton. Jacket foundations is a little bit is different, usually for deeper waters, and it rises above uh, the sea, and it has the structure like a jacket. We have three or four bases. Water depth in Europe, usually, if you look at it, most seas are deeper than 50 meters. Existing commercial foundations are not economically viable in deep seas. As we notice here, here is from 75 to 500. What we notice here is the 50 to 75, and this area we have below 50 meter depth. We have another structure we call it a floating wind turbine. That means we don't have the foundation, we don't have to stick to the ground, and this works very well in deep water. Here, what we have tension leg platform, we have weights here, and they're connected to spread and connected to underground. So in order to keep this wind turbine structure vertically. This is what we call it submersible, where part of it under and the other part is above. Here we call spar pi. And these are the structure of these foundation is usually laid down to the ground, but these are floating foundations. Floating wind turbine connection to the grid. This is another problem. Power stations. We get to it. Electrical cable. Substation. We have to have floating substation, and these are the wind turbine. And usually, if you look the status of Liberty, it's 305 foot. If we're gonna look at the wind turbine, it's usually between 600 to 800 foot. That's almost twice to three times the height of the Status of Liberty. That's very high. There is innovative wind turbine rotor. This is what we call it vertical axis wind turbine, where all the power electronics and the rotors are down here, and this is easy to maintain and repair. This is what we call a two-blade downwind turbine, and this is easily can face the wind and track the wind. This is what we call it segmented ultra morphing rod, where the structure here uh, can at high speed it can move faster. At lower speed, this can be stretched out and collect more power by facing the wind. We have another two type. One we call it airborne wind energy. This is experimental, where we have to, since the wind is very high at high altitude, so we have something flying up in the air with balloons and something like that. So this is how we can collect the wind, and this is experimental, just giving you a taste of the future. Well, here we go. We finished the wind energy lecture. What we have to think about, what are explained the basic principle of wind power generation. How is the maximum power produced from wind turbine? What are the main components of wind power turbine? What is the relation between power and the number of blades in wind turbine? What are